Go ahead.
Okay, so thank you very much for the introduction, and good morning, everyone. It's a great pleasure for me to be here to present my talk about my research directions. And my talk has a title From Saliency to the Camouflage Analysis. Do you hear me well? Awesome.
Yes.
So here is the outline of my talk. I will give a little bit about the background of the research, and then I will introduce two directions of my research, including salient object detections and the camouflage object segmentations. And after that, I will introduce my current research directions and with my future plan. So yeah, let's go. So we all agree that the computer is getting smarter and smarter, right? So like a long time ago, like 24 years ago, we know that computer defeated the chess grandmaster, Garry Kasparov. And I still remember at that time I was a middle school student, and it was really a big news to us humans because, you know, AI was able to defeat, the smartest guy in the world. And not long later, like 20 years later, and then we have the Google DeepMind, they developed the AI to defeat the Go Grandmaster. And it's really a big deal because you know that for the chess game, the board size only 8x8. But for the Go game, the board size, we have 19x19. So that means, you know, that they develop, you know, this is really a big improvement and achievement of AI against human. But the thing is, we know that AI is not our enemy. AI is our friend. And actually, computer or AI can replace human in some task. For example, computer can, just like I show you here, can operate certain tasks like looking at the markers, and then the robot can do some, you know, operations. Or we see that this is like the tool that we see very often in real life where you have the vacuum cleaner, right? So actually the vacuum cleaner is able to scan your home environment, and then it's able to keep your home clean. And I just show you a demo right here. You see that it works very well, right? And the vacuum cleaner works very well on the table. And then we can have the ping pong robot. And it's really a big thing because you know that not only predicting, you know, and try to detect the ball, but also try to hit the ball back and go through the net. So if you play ping pong or table tennis, you know that this is really a big thing. So how about computer vision? We know that computer vision contribute the big things here, right? Computer vision is able to see the markers, able to scan the environment, and able to detect the ball. And actually, computer vision aims to teach computer to understand the visual world. And we all know that one of the most notable features or, you know, a function that we know very well from computer vision is about the face detection, right? We have face detection everywhere on the camera or on the smartphone. For example, I take this photo. Actually, I didn't take it. Somebody else took it, but I use this photo. Do you know who they are? Of course, you know who they are, right? And then after that, I use the face detection, and I'm able to detect the faces from the photo. It works really well. But again, nothing is perfect. And sometimes the bad thing happens. That means we have computer vision is still far away from our human vision. I show you one example. Is there something wrong here? Tam, it's okay, right? The camera is able to detect the face. It's okay. No, it's not okay. The camera detects the face on the pillar, not the face of the person. Why? Maybe the hair just cover the face with the glasses, and in the meantime, you say the pillar with some texture like the eyes, the nose, the mouth. That's why computer vision, like face detection, only detect the face on the pillow. So we have a problem right here. What is it? Computer struggle to see as the human does. For example, if I show this photo to object detection, the object detection will say, hey, there's a car here. Do you see any car over there? Well, the car may be, you know, far away from the lake, right? It's not just like that. But how, but why does the system fail? If we look closely to this bounding box, and we take some features like crane features or the hawk features, and now we see the problem, right? I visualize this one right here, and this one look like a car, right? This one look like a car, and that's why, you know, the scene really tricked the AI or computer vision. Just recently, we read the news about this, something called OpenAI, and OpenAI is, you know, is performing very well against, you know, an image classification problem. So if I show this photo, to OpenAI and ask, hey, what is it? OpenAI will show, hey, this is a Granny Smith apple, right? It's perfectly fine, right? It's no problem. And then when I show this photo, hey, what happened here? I have the iPod written on the apple, and then the OpenAI understood this is an iPod instead of an apple. So you see that computer vision or object detection look at the object by you looking at the low-level features, just like the edges, or just look at the high-level features like the text, and they don't perform very well. So we really have the problem. And whenever we have problem, we have opportunity. This is my favorite quote from Robert Kiyosaki. Inside any problem, we have opportunity. So what can we do in this case? If we want to make computer vision to be as smart as our human vision, can we direct the way that computer sees and the way that us human does? Now I show you the visual saliency. What is it? Well, I show you this image, also called the stimulus in psychology research. When I show you this image, and may I ask you a question? What object is a salient object? What object is a main object? What object that catches your attention? Which one? Some people may look at the sky, I hope. Some people look at the trees. Some people look at the flowers. But I do agree that most of people will look at the house, right? The house. And in this case, the house is the main object. The house is a salient object because it's one catch our human attention. And saliency is the notion what is interesting to the world. The image, the scene, or the videos captures our human attention. Well, so can we teach computer to look at the way like human does? Can detect the main object? Can detect the salient object from the scene? The answer is yes, and we have a very long history. From the year of 1998, we have E.T. from USC. He developed a framework to detect the salient object or the saliency from humans. So given input image like this, and then he constructed the model by the winner-takes-all mechanism, and he able to predict the saliency map from the input image. And then the saliency map will be compared with the ground truth, which is the binary mask. That means we have the mask only cover the salient object. And then a few years later, we have another work from, of course, we have many works, and one of the notable works was from Achanta et al. In CPPR 2009. And it's trying to use the global information like the color information and the mean color information as well to compute the salient regions from the image. And then we have the big friend coming in. This is CNN, convolutional neural networks, right? And then thanks to the first work from AlexGris, and we know that AlexNet works very well in the task of image net classification. And we know that the image will go through all the layers in the network like convolution, ReLU, pooling, and then we end up with the fully connected layers. And then with the softmax, and we will get the score vectors, and then the class with a high score will be assigned to the input image. Just like I show you here, we have the image and the output. We have the class label. This is a car. And the question is, can we apply CNN to detect the salient object? Well, the input is an image, the output only one class label. It doesn't fit very well, so we have to wait for it. We have to wait for it. And the wait was not that long, okay? And especially we have another paper from Long et al. In 2015. This one about fully convolutional networks, also called FCN. So the FCN had upsampling layers, is able to produce the pixel-wise prediction at the output. And the thing is, we have inputs as the image, and the output we have also the image with the same resolution, and the pixel of the output is the same semantic classes. For example, we see that the blue pixels in the output for the dog, and the brown pixels in the output is for the cat. Oh, well, the input is an image. The output also the image, and each pixel for semantic classes. Hey, if we fine-tune this model with the data from the saliency, we will have the ground truth mask should be the salient object or not. And then we can, well, use this FCN for the task. And we're not the only one. So many people go for it and all in. So there are so many works using FCN to predict the salient object. like from the work from E and L on the left-hand side, and the work from 1L from the right-hand side. And there are so many works using FCN to predict the same object. And the next question is, what can we do to detect same object? Should we just fine-tune the FCN and to achieve better performance? So hereby I introduce the same object detection by using semantic priors. Before we go to that, I want to give the motivation. Well, we answered several questions. Who see the images? Who see the stimulus? Well, human, I think. And then who annotate the data? Of course, us, human, right? And is there any semantic information involved? Let's investigate it, okay? And actually, this is a paper that I published in the IEEE section of image processing, 2019. Well, we just revisit the stimulus I showed you before. I show you this image, and may I ask you a question? Which object is a salient object now? Hey, Tam, of course, we know this is a house, right? Of course, it's a house. The house is still the same object. And now I show you another one. What is a salient object now? Well, we have the house. Yeah, the house. Hey, we have the dog over there. And now the dog becomes the same object because I believe people pay attention more to the dog than the house. So the dog becomes the same object. Hey, what happens if I have another image or another stimulus? And what objects is a salient object now? The house, maybe. The dog, I look at the dog, but I don't think so. People look at the cowboy and the horse that he's riding on. So now the cowboy and the horse, they are the salient objects. Well, what if I show you this one? This one, the salient object is the house. Hey, what happens here? The thing is, when humans like us try to annotate the data to define which one is the same object, we have the priors, semantic priors, to identify which one is the same object, which one not. And what is the role of the semantic information in the saliency prediction? We have to figure it out. And also, can we understand the deep learning models in both explicit and the implicit ways? So we have a proposed framework for this problem. So here's the framework. We have the input image. We fit the image into the FCN model, and then we obtain the semantic score. And from that, we build the explicit semantic priors to obtain the explicit saliency map. And for another route, we over-segment the image into superpixels, and then we compute the implicit semantic priors to obtain this implicit saliency map. And from the explicit saliency map and the implicit saliency map, we try to fuse them together to have the final saliency map. Now let's go to the details. So we extract the semantic information from the image by using the FCN. So we put the image into the FCN, we have the semantic score, right? So now for each pixel x, y, we will have a vector, right? We have a vector. For example, if we have FCN trained on Pascal VOC, we will have 21 elements for the vector because Pascal VOC had 20 classes plus one class for the background. So we have 21 classes. So if we train FCN with MS Coco, we will end up with 81 elements because we have 80 classes in MS Coco and one extra class for the background. So we easily fuse, we easily obtain those semantic score for each pixel. Well, what happened to those scores? We can compute something called the explicit semantic priors by using this equation right here. So what does it mean for this equation? This equation means if this pixel belongs to a class like person, belong to a class like car, belong to a class like dog or cat, what is the chance that that object become the salient object? That means when we try to train the model, we have to get the cross-truth information. And based on that, we know, hey, if we have a dog, so most likely the dog will become the same object. If we have human, most likely the human can become the same object. If we have a potted plant, maybe it's maybe a same object. But this only works for one single instant. And we know that if we only have one single instant in the image, that instant should be the same object. But if we have so many instances in the image, what will happen? We need to compute the explicit simply price up every two classes. For example, if we have dog and cat in the images, or we have dog and human in the images, right? Based on the ground truth information that we gained from the previous step, we're able to know that, hey, if we have two instances from different classes, so that kind of instance from this particular class will get more attention than the others. And then for the testing phase, we compute the explicit saliency by extracting the similarity score, and also we multiply with the data that we gain when we train from the training data to obtain the explicit saliency map, I show you here in the slide. So we have the explicit saliency map. So that means input is image of the boy, and then we have the output is the pixels belong to the person class. I know what you're thinking now. What if the same object is not in the list of the semantic classes, right? Because we know that if we train the model on Pascal code, we have 80 classes. Or if we train the model on Pascal VSC, we have 20 classes. So some classes like, the castle or the houses I showed you from the beginning, they are not here, right? So how can the model handle those, class instances not in those classes that I list you to you here? Well, that motivates us to propose the implicit saliency map. So we have the image, and then from the image, we try to do over segmentation. That means we try to obtain the image regions or superpixels. And from the image superpixels, we extract the features like the color information, the texture information, and even like the mean similarity score of the superpixels. And then we train the random forest classifiers to map the extract features to the saliency value. Why we call this one implicit saliency map? Because it's implicitly map the features of the image region to the saliency values and based on the similar information as well. And for the testing phase, given input image, we also do the same thing. We extract the superpixels from the image, extract the features along with the similar information, and then we fit this kind of features into the trained random forest to obtain the implicit information. So in this case, you see that the implicit saliency map focus on to the hat and also the hat that the boy is wearing. And to obtain the final saliency map, we adaptively fuse the implicit saliency map and the explicit saliency map together by using this weighted sum. So what does it mean in this? It means that we have the alpha as the weight, right? And alpha is computed based on the percentage that this implicit object, the object in the implicit map contained in the image. So if we have mostly nothing in the explicit saliency map, that means the weight will be put more in the implicit saliency map. And now, why do we need to have two maps, right? One map should be good enough. Why we need to have two? I visualize several cases for you. So here, in this case, you see that for this example, you see that, hey, the explicit get the eagle out, right? Because it belongs to the bird class. And in the meantime, the implicit getting also the sky because, at the mountain because they obtain several salient features. But when we fuse them together, we only focus on the main object, which is the eagle. And this is a very interesting example. So we have the boy. Of course, when you perform the FCN, we only take the part of the boy, right? But also the boy is holding a tray. And the tray is well recognized by the implicit saliency map. And when we fuse them together in the adaptive way, we are able to have both the boy and also the tray together and as close as the ground truth. I mean, the last column that I show you over there. And the last example is very interesting because as I show you, the castle right here is not in any class list for both Pascal VOC or MS Coco. So that's why in the explicit map, we got mostly nothing. But for the implicit map, we're able to obtain the regions of the castle. And when fuse them together, we are able to have the castle region. And again, it's as close as the ground truth. And we know that, hey, just simply showing the example like this we cannot say our method is good or bad, right? That's why we have to do evaluation with the matrix, and we use precision and recall curve. We use MAE, the smaller the better, and we use also precision and recall with different adaptive threshold. And our method outperform all the baseline, and our MAE achieved less than 0.1. That's really a great achievement that year. And not only test our model on ECSSD dataset, we also test our model on HKUIS dataset. In this dataset, we have multiple instances in the same image. And again, our method still outperform all the baseline for all the matrix. You see that we have a red line for our method, and we have right here, and our method still perform better than the baseline. And this is the several images that I show you for different cases where our model perform very well to the input image. So we have the first column for the input images, and the second column for the ground truth, and the third column is from us. And then we can compare with the other baseline, and you see that most of the cases our model focus on the same object and very close to the ground truth. That's really great. Well, so we have very good model working on the saliency prediction. What can we use the result from the saliency prediction in the real life? And that's why I conducted another research about a review about the alternative system. That means the system using attention, using saliency result for the task. And for example, you see that if you have an image on the left, and then we try to resize the image to a small size, for example, but we don't want to crop or we want to shrink the image to have very weird aspect ratio. So how can we solve the problem? So we can detect the same object. In this case, we can have a father and child, and then we try to resize the image. We try to resize the image to keep the main object, but in the meantime, we can remove the non-salient region. And another example, like we can have NPR examples, like you have the image on the left, and you see that the main object, the same object here, we have a man with a guitar. So when we want to render the NPR, we can focus more on the man with the guitar. And we have so many with many applications with the saliency prediction. Well, yeah, it works well. But what's next? Is it the end of the story? Well, so the same object is the one that, outstanding, standing out from the image and salient. What happens if the main object is not salient? This is quite weird. If the main object is not salient, it's not a salient object. What is it? We are talking about the camouflage objects. I show you this example. Okay, we have 4 images right here. I took from MS Coco dataset. What do we have on the first image? We have like 3 people. Yes, the main object. We have the dog in the second one. We have the bird on the third one, and we have the fish for the 4th image, right? They all same object. We all agree, no problem. And now I show you the other 4 images. It's really tough because I have to pick, for the corresponding class, I have to pick the same image with the same class. You see? Are you able to detect something from the 4 images for the bottom row? Do you see something over there? And this is my favorite quote to my student in my class. If you cannot see anything here, that means it's time for you to buy a new laptop. But I hope that you don't buy a new laptop. Okay, so we have 3 people over here, right? Okay, and we have a person over here. Hey, that means if you have a dog here, right? This is you have a dog over here. How about the bird here? We have the bird over here. Well, how about the fish? The fish is my favorite. The fish is here. The fish is here. Wow. And actually those images I took from my old dataset. It's published on my website. And this is the work that we published in the Journal of CVIU 2019 as well. Well, we see that, hey, we have very challenging problem, right? With the complex object. It took us like human to spend a lot of time to figure out this complex object. Why do we need to have something called a camouflage object segmentation? Because We can use this in several tasks, like the animal preservation can be used in a search and rescue mission. So in those search and rescue mission, actually we human just like the passive camera object, right? Because we cover by by the background, and it can be used for surveillance system. So we have scene object versus camouflage object. So what do they have in common? We try to extract the object out from the scene. Yes, this is a common task. But the thing is, in the Saliency, the background is different from the scene object. Like in this case, we see the man right here. He's salient, of course, he's standing out from the image. How about the image on the right? So the background is similar as the camera object, or the texture of the camera object similar to the background. So it's hard for us human to recognize this. And how can we train computer to help us identify and segment the camouflage object? So we have to revisit the scene object segmentation problem. Why is this feasible? That's because we have so many data sets like MSRA, ECSSD, HKUIS, and MSI 10K. We have so many available data sets that leverage our training models, and it's kind of easy for us to do benchmarking and to know whether our method is good or not good. And also the scene objects have some common features like obvious edges, obvious contours, and outstanding colors. And those things cannot carry into the camouflage object segmentation because first, we don't have so many data sets in the problem. And second, the camouflage objects themselves have small scale and unclear edges or unclear contours. Well, what should we do first? So we have to define the problems, right? We have to define problems. So what are actually the problems in camouflage analysis? Well, Tam, if we have salient object detection, we name it camouflage object detection, right? Yeah, it seems right. But it doesn't seem right because we name it camouflage object segmentation. Why? Because the output here, we have the mask. We don't have the bounding boxes, just like we have in the object detection. So why people name it salient object detection? That's because in 2009, the Chanta called this problem salient object detection. That's why people after that just call salient object detection. Okay, but this is a good time for us to correct it. So we name it camouflage object segmentation because the output should be the mask from the camouflage object. And also we have camouflage object detection where we only focusing on the boxes. We try to detect the bounding boxes of the camouflage object. And also we also have another problem about the camouflage instance segmentation. We have so many problems to be solved in the camouflage analysis, and we focus on the first one, the camouflage object segmentation first. Okay, so we have the problem. We need to do the related works. And it turns out that this research field has been well explored in the literature. People care more about salient objects, about non-camouflage objects than the camouflage object. And we don't have so many data sets in the field to use for model training or for benchmarking. And the early work only focusing on the foreground and the background separation based on the color, intensity, and edges, all those low-level features. So where should we start? We should have a dataset first. So that's why the story begins. So we conduct and we collect a dataset named Camo Coco dataset. So this is a work published in CVIU 2019. Well, and the dataset are available on my website. And we have two subsets, one with the non-camo and one with the camo. Why we have this kind of setting? Because we all agree that in the image, we have the same object, right? But we're not sure that whether in the image we have the camouflage object, because the camouflage object not appear very often in the image, right? And from that, we try to collect the data from the internet. We use different kind of keywords, and we have a distribution of the data for our Camo dataset. So we collect the data from mammals, insect, bird, underwater for the marine life, reptile, amphibian, body art, and even for the soldier. And we tackle several challenges in the camouflage objects, like we have the object appearance, the background cluster, shape complexity, small object, object occlusion, multiple objects, and distraction. And finally, we collect the data with 2,500 images with all the manual ground truth mask for model training and also for benchmarking. Well, we finished the dataset. What should be the next step? Of course, we need a model, right? Because the dataset alone cannot help us to publish a paper. That's why we need a model. And here's the model that we have in the paper. We have something called the ANET. ANET is a short form of the Anna branch net for the camouflage object segmentation. Well, it looks cool, but why we name it Anna branch? I show you example about the Anna branch. So we have the river or the mainstream. And then the mainstream has another stream to split from the mainstream, and then the two streams merge later, much afterwards. So that means we have the Anna branch. We have a mainstream, and then we have another stream just split from that, and then after that, that split stream merge with the mainstream later. Well, now so that means in the Anna branch net we have two branches. So we have the segmentation branches and we have the classification branches. So what can we do with the segmentation branches? Oh, well, the input is an image and the output is a mask containing the camouflage object. Again, this is a binary classification problem, right? The camouflage and the output should be the camouflage object in the mask. Why don't we use available sensing model? Because they use very well. They use FCN model very well, right? And they fine-tune it to have very good result. Why don't we just fine-tune those available models to predict this camouflage objects from the scene? Well, it's finished for the segmentation branch. How about the classification branch? So I show you two examples. Of course, the top image is the one with the salient object. The image below is for the one with the camouflage object. Why with the bird from the top image is salient? That is because of the background. So that means the background can help us find and identify whether we have the camouflage object inside the image or not. So that is the motivation for us to build the classification branch. So this tries to answer the question like I told you, does the image contain any camouflage object? And we build a simple models with fully connected layers, and then with fully connected, and then with the submax to able to obtain the result whether we have the camouflage object in the image or not. For the evaluation purposes, we use MAE, the mean absolute errors. The lower, the better. We use F measure and the IOU, the higher, the better, to evaluate the methods. And we all know that our method, the method should be good enough, right? Otherwise, we cannot publish the paper. Yes, that is true. And you see that we do the benchmarking on our dataset, and we found that the ANET performed very well. And for the FCN models, of course, we have different results. And we found the SRM is the one that performed very well. And this achieved the state-of-the-art performance on our K-mod dataset. Well, this is good result, but any explanation for the uses of two branches? Well, I show you example right here. So if we only use the pre-trained FCN to find the camouflage object from the image, it didn't work very well, right? It didn't work very well. You see that right here. The pre-trained FCN didn't work very well. But if we fine-tune it with our data, we are able to do very, very good segmentation to have good result as the output. So that's very clearly that we use these fine-tuned models to have better segmentation. But why should we use the classification branch? I still don't get it. I still don't get it. Now I show you an example. We have the return FCN again here for the fourth column. The first column, we have the input image. Well, TAM, this worked very well for the cases, right? And in the meantime, TAM got nothing. Hey, TAM's wrong. And FCN pre-trained model works very well. Hold on. why the FCN works very well for those images. Because those images contain salient object, and FCN, pretend FCN here, works very well with the salient object. In our model, because we have a classification branch, so it helps us to classify that, hey, this is not the camouflage scene. So we output nothing, empty, just exactly the same thing like the cloud truth. So that's really show that the classification branch works really, really well in the case of segmenting the camouflage object. Okay. So is it the end? Is it the end of the story? Now we know that, hey, we work on the same object detection, and now we carry on to have the very nice problems about the camouflage object segmentation. Is it the end? The answer is no. It's just only the beginning. So right after we published the paper on CBIU about camouflage, we have another paper in CVPR 2020. They proposed COD 10K. This 10K here, it's just like the MSI 10K I showed you from the previous few slides, right? So actually that group, they saw our work and they say, wow, it's good to migrate from Saliency to camouflage object segmentation. And then they extend our data set from 2,500 images to 10,000 images. And then they add 3 new performance metrics into their work. And then they get one CR paper. And then after that, our group released another paper on archive. So we found that the bio-inspired network is very good for the camouflage object segmentation. What's the point here? The point here is, instead of fitting only one mainstream, we also fit the adversarial stream. That means we try to mirror the image. What's the point here? So that means when we take the photo of the camouflage object, so actually the camouflage object try to fool our human vision, right? But when you mirror the image, actually we just break that kind of the natural settings and just try to help the models to clearly see the camouflage object. That's why you see here, the mainstream cannot put this, but the adversarial stream can see the other things. And then we fuse them together, we are able to have very good result at the end, just like this. Is that it? No, it's not over. We have another work. So remember that we have a data set named Camo. And then later we have the paper, it's named Mocha. Wow, it's so cool, right? Camo and Mocha. So this one from Gisman's group in ACCV 2020. What is it? So they realized that if we can have Camo on images, why don't we just have another data set on moving camouflage object for the video? So because of that, they collected 141 videos with 37,000 frames. And this is the largest video data set for the camouflage animals. Wow, that's so cool. What else? So we have another work from Ren et al. So they try to learn the deep texture-aware features for the camouflage object detection. And also we have the camouflage segmentation published in AAAI. That means we use the our Camo data set, and then we label at the binary mask for the instant level. And after that, we are able to detect the instant, the camouflage instant from the image. And recently we have one paper, it's called Camo++. So it's under review for the TIP, and we passed the first round with the major revision, and we are working on the revision. So we collect a new data set for the instance. We know that 2000 is not good enough. That's why we collect more data, and then we label at the instant level. And with different keywords and to that was our data set. And we got very good feedback from the reviewers. Okay, and not only for the saliency and the camouflage, I also do some other research. Like I got a funded project from NSF. It's called the Crowd AI Sensing-Based Traffic Analysis for SCMC Planning Simulator. So what is it? So we know that when the city leaders, they want to develop the city, they want to add a new bridge, to add a new road, to change any direction of the traffic, they need to have the simulation. And to have the simulation, normally they use the mock-up data. But what happened if we collect the data from the real life traffic cameras, and then those data can be used to help us know that, hey, if we add a new bridge, a new road, or change the traffic direction, so what happened to the traffic? So the camera, the model will update the traffic graph and able to visualize it in the simulation. And this is like 2 years project, and we got it last year. And we get another project funded by the LAMP Research about a crystal growth. And I was very happy to know that Dr. Shah got for the project about this crystal growth as well. Okay, so in the crystal growth, we have several phases, like the meltdown, stabilize, seeding, necking, crown, body, tailing, pop up. And if something wrong happen, like in the body or in the ground stage, and then we have to reset the entire process. Hey, is there anything that we can use for AI or computer vision here? The question is right there. We have a camera, and the camera is looking at the grower, and the camera is able to show us the scene. And the thing is, if something wrong happened and we can detect earlier, we can save a lot of costs for the LAMP research. So that's why we got a funded project. We try to see when the things goes wrong and how can we prevent it. I also conducted several research like the image synthesis, the face analysis, like the people wearing masks, and we try to estimate the age or the gender or the expression throughout the mask. And then we also do the video analysis, and we do the mixed reality applications like the VR or AR. So I believe that the AR, VR should be a very good application domain for computer vision algorithms. So for the future plan, so I am looking at artificial vision, the merge between the artificial intelligence and computer vision. I want to conduct research in computer vision, just like the one I showed you about the camouflage object segmentation. And of course, we need big data for the models, and we should have the interactive media. I mean, the models can interact with us, human. And of course, we must have deep learning, because deep learning should be the future. And for the potential funding, I'm looking at the NSF, of course, and I know that UCF achieved a lot of fundings from REU, and I also looking at the SCC, RI, SACC, and also the funding may come from DARPA, AFRL, or ONR, and even from companies like Google, Facebook, LAMP Research, and DDA. And I want to say thanks to my previous and current collaborators. Like I learned a lot from them, like Dr. Nguyen, Dr. Hali, Dr. Feng, Dr. Zhao, Dr. Du, Dr. Graham, and Dr. Subopeda. And I hope that after the talk today, I can have future collaborations with you, with like Dr. Shah, Dr. Mahalanobis, Dr. Rawat, Dr. Lobo, Dr. Farouche, Dr. Ranawat, and Dr. Moore. And the good thing I love from this slide is that all of them are smiling at me and smiling at you. So that's it. Thank you very much for your time and your attention. Thank you. And it's time for the questions, please.
Excellent, Tom. Are there questions? So let me ask a question here. You know, so your talk shows that you can find things that are extremely difficult even for humans using the saliency approach. Does this help? And for the most part, you know, you are talking about, which is I think the more important problem, the objects in the foreground, the ones that we consider important. What about actually repurposing that in some sense to deal with very diverse backgrounds? Is there a version of this that will allow, let me see how I can say this. Like human beings, you know, we can easily understand what the most important salient foreground object is, but we can do that in very, very diverse background areas too. Is there a dependency of your algorithm on the complexity of the background as to how well it does on the foreground objects?
Yeah, thank you very much for the questions. So I go back to this one. Yes, so we also consider the diversity of the data. So that's why we have like the clutter background as well, just like I show you here. So the thing is, the camouflage object is considered as the camouflage object when it's inside certain environment. For example, like I show you, if the bird on a tree and it's not camouflage anymore, but if the bird just on the ground and then covered by the leaves, and then it becomes the camouflage object. So this means it's like, so that's why we call this one like artificial camouflage and the natural camouflage. So for example, like human like us, like if we have soldiers and the soldiers try to hide themselves, right? So they become artificial camouflage. But in nature, we have a lot of animals, like they try to hide themselves, they try to conceal themselves in the natural way. Yes, we do consider the clutter background, just like I show you here.
Okay.
Thank you.
The reason I ask is because I work kind of in a aerospace DoD kind of background, and there's a lot of interest in being able to find objects, because if the object is visible, that's pretty that's difficult enough. But in the defense applications, they actively use camouflage to try and hide it.
Exactly.
And although these are very natural objects, I think I don't know if you've had an opportunity to share this with places like ONR or DARPA or Air Force, but I think this would be extremely relevant.
Thank you very much. Yeah.
For finding things that are purposefully camouflaged to blend in.
Sure.
It's very, very impressive. Any other questions? Okay. All right. So I think we'll have an opportunity to, of course, talk with you more in detail later on in the afternoon. If there are no other questions, I'd like to take this opportunity to thank you, Tam.
Thank you so much.
Yes, and I think there's a lot of information here. I'm going to actually ask my student, one of my students who was not on the seminar right now, to look at your talk, because it's directly relevant to some of the work that she's also doing. So I may be following up with you more later. Well, with that, let us thank the speaker, and we'll look forward to seeing you at the next meeting.
Thank you so much, and have a great day all. Thank you.
Okay, bye-bye.
Bye-bye.